So in the last lecture, we have discussed some numerical problems. Okay, I think this was the numerical problem which I discussed in the last class. You have seen the recorded lecture. So was that clear? Was there any problem in that? Am I audible to you?
Yes,
Yes,
sir.
yes, sir.
Okay,
it was clear.
it was clear. Okay, all right. So yeah, so now I'm going to discuss about uh, some other topics related to the first law of thermodynamics only. So specific heat at constant volume. We discussed about it earlier also, but here I am going to give you the equation for the uh, specific heat at constant volume. So now you remember that in case of constant volume process, if we calculate the value of the heat transfer, see this shows the constant volume process. The value is equal to change in internal energy because in case of constant volume process, the value of delta W is equal to 0. So that means this value is equal to mCv T2 minus T1. Somebody wants to join, wait. So this is heat transfer at constant volume, which is equal to change in internal energy, because the value of work transfer, PdV work, is 0 in this particular case. And I hope that you remember the value, remember the definition of the specific heat. Specific heat means heat required to raise the temperature of a unit mass of a substance through unit degree Celsius or unit degree Kelvin. Okay, so it means if you have a substance, suppose there is a substance like this, and its mass is 1 unit, and its temperature is raised by delta T, which is equal to 1 unit. Okay, then whatever is the amount of the heat which we require to give it to it for raising the temperature of the substance through 1 degree is actually known as the specific heat. And when we keep the value of the volume constant, then that uh, heat transfer is actually known as, then that value of specific heat is known as specific heat at constant volume. Now you can see here in the first equation which I have written here, this is the first equation which I have written here, the value of Q is equal to change in internal energy. Okay, so I can always write from here that du is equal to mcv dt. And if I want to write it on unit mass basis, then it is du cv dt, because now I have divided the both sides by mass. Here it is the total internal energy, and here it is the specific internal energy. Okay, so from here if I calculate the value of cv, the value of cv comes out to be del u by del t when the volume is kept constant. So that means this is the relationship, or this is the equation for the specific heat at constant volume. I think somebody wants to join, so wait. So the value of cv is actually equal to del u by del t at constant volume. Probably you may not be needing to use it in this particular course actually. Okay, this is just for information. You should remember it. Now, if you see in this particular equation, U is a property, temperature is a property, volume is a property. So the value Cv, or the specific heat at constant volume, this is also a property. But basically you need to remember only one formula, which is equal to Cv del U by del T at constant volume. Now, if we multiply this CV is specific heat at constant volume. If I multiply it by mass, then I will get heat capacity of the system at constant volume. Okay, so here it is capital C, here it is small c. So that is the difference basically. So you know that if it is a small alphabet, we are using it for intensive property. If it is a capital alphabet, it is for the extensive property. So you can see the units also for the specific heat, kilojoules per kg Kelvin or joules per kg Kelvin. You multiply this by mass, then the value of heat capacity unit will be joule per Kelvin or kilojoule per Kelvin. So it's quite simple. Now let us talk about a property which is enthalpy. So enthalpy is actually given by capital H, and if I write specific enthalpy, it is small h. So we are going to discuss about enthalpy and specific enthalpy. Now, how do we define specific enthalpy? Normally, there is not any particular definition for the enthalpy. We usually define it with the help of a formula, which is written here. H is equal to U plus PV. Okay. So if you see here, this U is the specific internal energy, P stands for the pressure, and V stands for the specific volume. So V is specific volume. All other terms are clear to you. Small u means specific internal energy. Okay. And if I want to calculate the value of the enthalpy, then I have written here capital U plus PV. Okay. So here this V is actually volume. So volume in meter cubes. If it is specific volume, it is meter cubes per kg. So otherwise what I can do is I can also write enthalpy, which is equal to M into H. Now this H is the specific enthalpy. So it is equal to M into U plus PV, and capital H will be given by, when I multiply M and U, you get the capital value of H, that is internal energy, plus P into capital V, where V becomes the volume. Okay. So now you can see it here once again, like we talked about the uh, here we talked that CV is a property because U, T, and V are properties. Similarly, when we talk about enthalpy, H is equal to U plus PV. Okay, just 1 minute. Somebody wants to join. Now U is given by CV into T, and PV is equal to RT. Okay, so that means if you will see here, see once again somebody wants to join. See, actually, people should join early. Actually, it's already so. Please listen, all of you. Today I am allowing you to join late also, but actually it disturbs my momentum when I am in the class. So it's my request to all of you. All of you should join by say 5 6 minutes after the start of the lecture. So if you join within 5 6 minutes of the start of the lecture, it will not means break my momentum. Otherwise, it's very difficult. Now I will not allow anybody to join now. So H is equal to CVT plus RT. Okay. Now you see, if we talk about the enthalpy, CV is a property and it's an internal energy. So it's a function of temperature. Similarly, in that RT also there is temperature. So basically we can say the enthalpy or specific enthalpy is a function of temperature. So once again, for your purpose, you should remember this equation, which is equal to H is equal to U plus PV, or capital H is equal to capital U plus P into V. What is the unit for enthalpy? You remember the unit for U is kilojoules per kg. So same is the unit for enthalpy. If you talk about capital U, the unit is kilojoules. So the unit for enthalpy is kilojoules. Okay. So that is what I wanted to tell you about the enthalpy part. Now let us discuss about the specific heat at constant pressure, CP. Okay. Now we know that H is equal to U plus PV. I just told you that enthalpy is a function of temperature, and it is given by H is equal to U plus PV. And I also know that from the first law of thermodynamics, delta Q is equal to dU plus PdV. This is the first law of thermodynamics for a process. Yeah, once again there is somebody. Just wait. So, if I calculate the value of delta Q at constant pressure, you remember that the equation was equal to, the equation is actually Cp into dt if we are taking it on the unit mass basis. And if I write the value of delta Q from this particular equation, the delta Q is given as du plus pdv. Okay, du plus pdv. So I have replaced this value of delta Q by du plus pdv. That comes out to be equal to Cp dt. Now let us focus here. This is H actually. I can differentiate this equation. So this will become dH. The second term will become du, and PV. If I differentiate PV, there are two parts. So the first part will be PdV when I am considering P as the constant, and the second case V will be kept as constant. It will be VdP. And for a constant pressure process, what will happen to the second term? This term will become 0. So I can say that dH is equal to du plus pdv. Okay, du plus pdv. Now you see this here. It is du plus pdv, and this value is also du plus pdv. And du plus pdv is actually equal to Cp dt. So this is Cp dt. So from the left side and the from dH, this term and this term, I can always say that the value of Cp is given by del H by del T at constant pressure. Okay. So Cp is nothing but Cp is equal to del H by del T at constant pressure. Once again, if you see the value of Cp, uh, you have enthalpy, specific enthalpy in the numerator, temperature in denominator, and pressure. All these three are properties. H, T, and P are properties. So Cp is a function of temperature. And if I take multiply this value of Cp by mass, then I will get capital Cp, and it is actually heat capacity at constant pressure. So once again, not to worry much, you need to remember this equation only. Now let us talk about the energy of an isolated system. We discussed about the isolated system in the first lecture. What is an isolated system? An isolated system is one in which there is no interaction of the system with the surroundings. No interaction. Just remember this. So for an isolated system, when there is no interaction here, what will be the value of delta Q? The value of delta Q will be equal to 0 because it is not interacting with the surroundings. So there is no heat transfer. When it is not interacting with the surroundings, the value of delta W will also be 0. That means there is no work transfer. And if I write a first law thermodynamics for a process, means I am considering that the isolated system is undergoing a process. So this is the equation for that. And if I see the values of delta Q, this delta Q goes because it's 0, delta W goes because it's 0. So I am left with dE, means change in energy of the system. Which system? Isolated system. Change in energy for the isolated system is 0. That means if I differentiate this equation, energy remains constant. So for an isolated system, the energy remains constant. the energy always remains constant. So basically, because there is no interaction of the isolated system with the surroundings, that is why the value of heat transfer and work transfer is zero in that particular case, and the energy of the system will remain constant. So these are simple concepts. Now let us talk about perpetual motion machine of first kind. See, we have discussed about the first law of thermodynamics. Okay, we have discussed about the first law of thermodynamics, and what is the PMM1? Just wait, somebody wants to join. Now let us see what is first law. First law is the conservation of energy basically. That means energy is neither created nor destroyed, but only gets transformed from one form to another. Means you can convert the mechanical to energy to electrical and so on, or electrical to mechanical and so on, or heat energy. Now let us see. This is the statement of the first law of thermodynamics. Can there be any machine which can continuously supply mechanical work without some form of energy disappearing simultaneously? Means if you have a machine in which you are not inputting any energy, you are not giving any energy into the machine, but still it is giving work to us. There can be no such machine actually. So uh, here if you see on the right hand side, there is a diagram of PMM1, perpetual motion machine of first kind. And here we have a engine which is shown here. Now what is shown here is that this value of Q is actually equal to 0. Means we are not inputting any heat energy into this engine. Okay, and still this engine is giving us some finite work. Is it possible? It is impossible. So that is why it is known as a PMM1, perpetual motion machine of first kind. That means it cannot exist actually. So it is written here, there can be no machine which would continuously supply mechanical work without some other form of energy disappearing simultaneously. So which form of energy should simultaneously disappear? Means we are talking about Q, and in this particular case we have considered Q is 0. So when Q is 0, there is no question of disappearance of the heat energy. Rather, we are supplying zero heat input into this engine, but we are getting some finite amount of the work. So that means such a machine cannot exist. And if you have understood, if you know about the concept of the efficiency of a heat engine, I don't know whether you know efficiency or not, but efficiency is always given by output divided by input. Output is some finite value, okay, whereas the input is 0. So it will be infinite, and that is impossible to have a infinite efficiency of any machine. You think about your own bodies actually. See, when we supply, when we take food actually, that food is has the chemical energy that is converted to the, that is digested, and that gets converted to the heat energy, and we are able to do certain amount of the work. But can we convert that whole energy into work? No, it is not possible. We have to reject certain amount of that energy of the food into surroundings also. Okay, so it is never possible that the efficiency of a any machine is 100% also. You cannot have 100% efficiency also. But here what we are saying is that this machine is having an infinite efficiency, so it is impossible. So such a fictitious machine is called perpetual motion machine of first kind, or in brief we can say it is PMM1. A PMM1 is thus impossible. So I have explained you why it is impossible. Now it says the converse of the above statement is also true. That is, there can be no machine which would continuously consume work without some other form of energy appearing simultaneously. So it means, no, It is the converse of the premium one. So what it says is that suppose we are supplying some finite amount of work, okay, and this value of Q is zero. So this is also not possible. So this is the converse of the this particular machine. Okay. The, if this is machine one, then machine two is converse of machine one. Okay. So both are impossible. Now, what is the limitations of first law of thermodynamics? See, first law of thermodynamics deals with the amount of energy of various forms transferred between the system and its surroundings, and with changes in the energy stored in the system. So let us try to understand it once again. The first law deals with the amount of energy of various forms transferred between the system and its surrounding. So see, we know the first law of thermodynamics is actually equal to delta Q is equal to delta W plus du, or sometimes in place of du we also write dE. So basically this the first sentence of this line says energy of various forms transferred between the system and its surroundings. That means we are talking about delta Q and delta W only, and with changes in the energy stored in the system. That means we are talking about dE, or the energy part. So basically this is already known to you. It treats work and heat interactions as equivalent forms of energy in transition. So it doesn't basically discriminates between the two. It says both are equivalent forms of the energy, and does not indicate the possibility of a spontaneous process proceeding in a certain direction. Okay. So basically, see, this is a very important statement. This is a very important statement. Basically, in when we are talking about the first law of thermodynamics, it only says that heat can be converted into work and work can be converted into heat. Okay, because it is the law of transformation of energy. Okay, it says one form of energy can be transferred to the another form of the energy, but it never says that in which direction the process should occur actually. Okay, see, all the spontaneous processes occur in a particular direction. Okay, you must have seen uh, suppose okay, I will talk about it when I am talking about the second law of thermodynamics. I will explain it more actually. It is the second law of thermodynamics which assigns a quality to different forms of energy and also indicates the direction of any spontaneous process. So for the time being, uh, you may not have understood this particular line, but I will explain you when I will teach the second law of thermodynamics, and that will take 3 4 lectures more, and after that we will be reaching to the second law of thermodynamics. Okay, so for the moment you should always remember that the first law of thermodynamics says that energies can be converted from one form to another, like it says that heat can be converted into work and work can be converted into heat. That is what the first law says, but it never tells whether if there is any process, whether that will take that is it possible for that process to take place in a particular direction or not. Okay, I would give you an example here actually. For example, suppose we have a say, you can say there is a swimming pool here. Okay, we have a swimming pool here, and there is a man which is standing here, and this is a he is going to jump here. You know that if he would jump he will go down, but in movies you must have seen that the man is coming out from the swimming pool and landing here. So you understand which process is possible. If a man jumps from a platform on the from the top into the swimming pool, that is a possible process. But if you have seen a man which is coming out from the swimming pool and going back on the platform at a higher level, it is a impossible process. So in a similar way, The second law of thermodynamics tells us that um, the process will occur in a particular direction. I will give you one more example. For example, you have uh, a cup in which there is tea, okay, and the temperature of the tea is, let us say, 70 degrees Celsius. Now, what will happen? Because this cup is open, okay, this cup is open, so the heat transfer will take place to the surroundings, and after a certain period of time, the temperature of 70 degree will drop to 30 degrees Celsius. Now, what will happen in this particular case? Yes, this process is possible because the heat is lost by the tea, because this heat is now going to the surroundings actually. Okay, it is going to surrounding. But is it possible that you have a this tea cup with you now? Now it is containing tea at 30 degrees Celsius. Outside is also at 30 degrees Celsius, and automatically the heat transfer takes place from here, and the temperature of the tea rises to 70 degrees Celsius. Is it possible? It is not possible. So that means because the process takes place in a particular direction. See, the first law of thermodynamics does not put any restriction on any process that in which direction it will proceed. It does not tell us in which whether a system can go from a particular state to the another state. It will not tell us. But yes, it will say that heat and work are mutually convertible into one another. So this is the limitation of the first law of thermodynamics. Okay, we will discuss about it in more detail. Now I am going to some numerical problems here. This is a very simple numerical problem I discussed in the last class also. So what you can do, uh, you can have a print screen of this problem. I won't be discussing it. I will be going to a higher level problem. Okay, and will explain you. You can take a print screen. Okay, you read it. If you are unable to understand it, you can ask. Yes, this is a process. This is a another example, which is a better example. I think somebody wanted to join. Let me see. I am also allowing you people because most of you say that there is a problem of internet. So that is why I allow you people. Okay, now let us read this numerical problem. Uh, you see, when a system is taken from state point A to state B, as shown in figure 4.2. So where is the state point A? State point A is here, and this is state point B. Along path ACB. So ACB is the path. So that means we are going from here to here along this particular path. So first of all, from we are going from the system is moving from A to C, and from then it is moving from C to B. This is how the process is taking place. And then you can see the system is coming back to the original state via this particular path, and the cycle is ending at point number A. So it says along path ACB, 84 kilojoules of heat flows into the system. Okay, so 84 kilojoules of heat flows into the system. That means it is positive. So you can see it here. We have written it here. QACB means heat transfer into the system during the process ACB. Okay, is 84 kilojoules, and system does 32 kilojoule of work. System does 32 kilojoules of work. So you can see it here. We have written here WACB is equal to 32 because it is system which is doing the work. So that is why it is taken as positive. This was the heat which is entering into the system. That is why it has been taken as positive. Okay. So once again to remind you about the sign convention, if this is the direction of the work, then it is considered as positive, and if this is the direction of the heat, then it is considered as positive. Otherwise, it is the negative actually. It is negative work and negative heat transfer if they are in the opposite directions. Now, how
Could you
much?
just say that again?
Okay. See, you can see it here. I am considering this as the system. This dots, I am considering there is some gas within the piston and cylinder. Okay. and this gas is considered as the system. If the heat is entering into this system, heat is going inside the system, then it is considered as positive. And whereas if it is the work which is leaving the system, that will be considered as positive. Otherwise, suppose if I have the similar system here, okay, and what is happening that heat is being lost to the surroundings. Now you can see the direction of the heat transfer has changed. It is considered as negative. Similarly, if it is the work which is entering into the system, this will be considered as negative. Okay, so that is the sign convention. Did you not attend the previous classes? Okay,
No.
okay. So let us see. So we are given with the two quantities here. Heat transferred into the system is 84 kilojoules and work transferred into the system is 32 joules along the path ACB. Okay, this is given to us. Now it says how much will be the heat that flows into the system along path ADB. So we have been asked to calculate the value of Q, A, D, B, means along this particular path. This is the path A, D, and B. Along this path, we have to calculate what is the value of the heat transfer if the work done is 10.5 kilojoules. So this value is given to us, work done. So this is basically work done by the system. So that means we are given with this value WACB. Okay. No, no. We are given with this value. This value WABD. This value is 10.5. Okay. This value is given to us. So basically, just try to understand it. Now, what we can do is, it is we have to calculate heat that flows into the system. So we have to calculate this value QADB. That is what we have to calculate. Okay. So first of all, what we can do is, now if you see this particular process is happening from A to B. Okay. You can go either from here to here or you can go from here to here. Now, because the initial and the final states are fixed, what will be the change in the internal energy? Whether you go via the path ACB or whether you go via the path ADB, it will remain same. So what we will do, we will write this particular equation QACB is equal to UB minus UA plus WACB. WACB is already given to us here. Okay, so using this equation, what I can do is I can calculate this particular value. Okay, UB minus UA. Now, the value of QACB is given as 84 and WACB is given as 32. Okay, so this is 32 and this is 84. So I can always calculate the value of UB minus UA from this particular equation. And which is this equation? Can anybody tell me? See, this is the first law for a,
Yes.
it is the for a process. Okay, it is the first law of thermodynamics for a process. Okay, so we have used that and we have calculated the value of UB minus UA, which comes out to be 52. Okay, 52. Now what we can do is, we have been asked to calculate the value of work or heat that flows into the path ADB. So once again, I can use this particular equation for the path ADB and I can write QADB is equal to UB minus UA plus WADB. Okay, and WADB is given to me as 10.5. Okay, and UB minus UA I have already calculated here and I can put its value here and then I will be able to calculate the value of QADB, which comes out to be 62.5 kilojoules. This is the first part actually. All right. The second part it says is, you read it from here. When the system, just a minute. when the system is returned from B to A along the curved path, the work done on the system is 21 kilojoules. Okay. Does the system absorb or liberate heat, and how much of heat is absorbed or liberated? So we have to calculate the value along this particular path from B to A along this particular path. Okay. We already know the value of UB minus UA. That is already known to me. Okay. But I have now been asked to calculate what is the value of the heat transfer during this process. Okay. So once again, because it's a process, UB to A, okay, it is equal to, this is the final value minus initial value of the internal energy. So this is delta U plus W along the path B to A. Okay. Now, uh, can you tell me one thing? When we calculated this value of 10.5, okay.
Yes, yes.
Mm-hmm. Just a minute, just a minute. Are we given with W? Yes, W WBA. This is given to us as, you can see it in the question, it is given as 21. Okay. So what we can do is we can put this value and the change in internal energy. Now, actually we were given this value as 52, but that value was for UB minus UA was given as 52. If I calculate the value of UA minus UB, that will be equal to minus 52. So I can put it as minus 52, and the value of WB to A, work done on the system. So that means this value is negative. So minus 21. So the total value of heat transfer from B to A is minus 73. So it means the system liberates 73 kilojoules of heat. So that means the heat is leaving the system. Okay. Now let us go to the third part. What is asked in the third part? When the system is taken from
It's
yeah, C part. Just a minute. If UA is equal to 0 and UD is equal to 42, find the heat absorbed in the processes AD and DB. So which is the process AD? AD is this process and DB is this process. Okay. So we have to calculate the value of AD and DB in these two processes. So first of all, I would like to know from you, if I take this particular process BD, what will be the value of W in this particular case? Here, W D to B. What is the value? Can anybody tell me? You see, it is a
it will
PV
be
diagram.
0.
It is 0. Okay. This value is 0. Okay. And this is basically WAD. Okay. So now, when I calculate this value of WADB, ADB means for this particular process plus for this particular process. For these two processes, this should be equal to WAD plus WDB, but that is equal to WAD only. And for this total process from here to here, for this whole process, the value of the work was is 10.5. It is given in the previous statement. It is written here. If the work done is 10.5 kilojoules, this is already given in the statement A along the path ADB. Okay, so this work is already 10.5, and the value of DB, this work was 0. So that means the value of WADB AD will come out to be 10.5 only. So the work along AD is already known to me. So what I can do is I can apply the first law of thermodynamics for a process, that is QAD is equal to UD minus UA plus WAD. Okay, so QAD will be equal to UD minus UA. Now what they are saying is the value of UA is 0 whereas UD is 42. So we can put these two values plus 10.5. So this gives us the value of the heat transfer 52.5 kilojoules.
Iya ya, aqui desliguei que é. Professor, tá explicando.
Yes, any questions?
Thank you so much for the call, I guess. Thank you. Those cool, I guess.
Okay, let us proceed further. Now we have to calculate the value of uh, QBD. This is the value which we have to calculate. For this particular process, we have to calculate the value of heat transfer for the process dV. Okay, here. So I know that QADB is the whole process. Okay, the value of heat transfer during this process is 62.5. This we calculated previously. You can see it here. QADB. This we calculated here. Okay, so it is 62.5. So that is equal to sum of QAD plus QDB. And QAD we have just calculated as 52.5. QAD is calculated as 52.5. So we can put it here. So yeah, for AD we can put it here, and here with the value of QDB can be calculated, which comes out to be 10 kilojoules. So what you can do is this numerical problem is given taken from the book only. It is example 4.2 from the chapter. So you can read it from there and try to understand it if you have not been able to understand it right now. Okay. Now let us.
Yeah, yes.
Yes, tell me.
Yeah, I say yes. What you
Okay.
have said.
Okay. All right.
Hello, sir.
Yes.
Could you resend the book for the purpose of the new students, please?
Okay. There are two persons who are the admins. I will ask them to send it. Okay. So please send. I think Ali is there. Hmm?
Okay.
Okay. Ali, can you send it?
Uh, what I we said?
Book. I think I have sent the book in the class. Yeah, just a minute.
Okay, okay.
Sir,
Yes, yes.
no problem. We will share each other.
Okay, I have resent it.
sir,
Okay. I
I
have shared.
have question.
Okay. Now let us
Sir,
see this numerical problem. Uh, Air is initially at 260 degrees Celsius and 700 kilopascal. Okay, and occupies 0.028. Just a minute. Okay, so air is initially at 260 degrees Celsius. So that means the initial temperature T1 is 260 degrees Celsius. Pressure is 700 kilopascal, and occupies volume V1 is equal to 0.28 meter cube. This is given to us. A polytropic process with n is equal to 1.5. So it is a polytropic process which is taking place, that is PV raised to power 1.5 is equal to constant, followed by a constant temperature process. So first process was polytropic, the second process is temperature is equal to constant, which completes the uh, initially it was written the air is expanded at constant pressure. So before the polytropic process, the first process is actually pressure is equal to constant. So this is the first process, polytropic process is the second process, and constant temperature process is the third process, and it completes the cycle. Okay, and there is this value of volume also during the expansion, it is given as 0.084. All the processes are quasi-static. Consider the air is in a expanding in a cylinder piston device. Find the pressure, temperature and volume at all salient points of the cycle. Calculate W, Q, delta W for each process. Sketch the cycle on PV diagram. Okay, so we have to calculate the values of pressure, volume and temperature corresponding to point number 1, 2 and 3. Okay, and we also have to calculate the value of W, Q and delta U, and we have to draw the PV diagram. Okay, so this is what we have to do. So let us draw a table for this. So here what I have done is I have made a table first of all. Now what is the process 1 to 2? It is a constant pressure process. Process 1 to 2. Process 2 to 3 is a polytropic process with the value of n equal to 1.5. This is equal to constant. The third is the process 3 to 1. In this process, temperature T is equal to constant. Okay. So when I say the pressure constant during the process 1 to 2, I can say P1 is equal to P2. And similarly, if it is the process 3 to 1 during which the temperature is constant, I can say that T3 is equal to T1. So this information is already given to me. And here in the state points, what I have done, I have uh, written it in the form of a table. So it would be easy for me to understand which are the values which are available to me and which are the values which are not available to me. So at state point 1, pressure is 700 kilopascal, temperature is 260 degrees Celsius, and the volume is 0.028 meter cubes. Similarly, at the state point 2, because the first process is constant pressure, so the pressure will be once again 700 kilopascal, and the volume in the isothermal, in the isobaric process, which is shown here, you can see here, it is 700. This is 700. Okay, this is a straight horizontal line. Here the volume is 0.028 and the final volume is 0.084, and this is a constant pressure process from state point 1 to 2. Okay, so this value of volume is given to me. Once again, when you see it here in the numerical problem, air is expanded. Whenever the air is expanded, okay, there can be two things that can happen. If the pressure is remaining constant, then the volume will increase. Okay, or if the volume is remaining constant, then the pressure will drop. But in this particular case, the pressure remains constant. That is why the volume is increasing. So this is the value of the volume. Then finally we are given with T3 is equal to T1. So T1 we have written as 260, and here T3 is also 260. So we have certain unknown values here, here, and here. These three values we have to calculate. This is the temperature T2, then this is the pressure P3, and here it is the volume V3. These are the three parameters that are still remaining that we have to calculate. This is what has been asked in the question. So let us see it here. Once again, this table is shown here so that you don't lose the track of the question actually. Now the first process, as you can see, is constant pressure process here. Okay, and we are given with the temperature and the volume. So for a constant pressure process, if the pressure is constant, we have the relationship. Which is the relationship? V1 by T1 is equal to V2 by T2. And from here, I can always calculate the value of T2, which is required here. This is unknown value. So T2 will come out to be V2 by V1 into T1. Now I know the all other parameters. You can see it here. Just see it carefully. V2 is already known to me. The value is 0.084. V1 is also known to me, the value is 0.028, and the temperature which has been considered here, this is taken in now kelvins. Okay, so the temperature here was 260 at state point 1. I have converted this value in Kelvin by adding 273.15. So after doing this calculation, I get the value of T2 as 1599.45. So once again, I have repeated this table here. Now this value has been calculated and these are the two missing values. Okay, so let us go to the next slide where I have calculated these values once again. Now the second process was polytropic process with PV raised to power 1.5 is equal to constant. Now we have already calculated this temperature 1599. Okay, and process 2 to 3, you can see the temperatures is known here, but here the pressure is known, and here this pressure P3 is unknown. So we should have a relationship between pressure and temperature so that we can calculate the pressure P3 actually. So for calculating P3, we should have a relationship between pressure and temperature. And if I want to calculate the volume V3 for the polytropic process, then I can use some other relationship. Let us see how we have done it. So you can see it here. See, P2 V2 raised to power n is equal to P3 V3 raised to power n, but neither P3 nor V3 is available. Both these values are unavailable to me. This temperature is 1599.45. So this is not known, this is not known. So we should use TV raised to power n minus 1 is equal to constant, or P divided by T raised to power n over n minus 1 is equal to constant. So you can see, if I will be using this particular equation, I have the value of the temperature, both the temperatures which are given here, 1599 and 260. Okay, both these temperatures are known to me. And if I will use this particular equation, then I have the value of the temperature, but the one of the pressure is known to me and other temperature pressure is unknown to me. So I can use this particular equation. I can say that T2 V2 raised to power n minus 1 is equal to T3 V3 raised to power n minus 1. And from this particular equation, I can always calculate the value of V3. You just read it carefully how I have done it. So I have brought this V2 in the denominator here, and then I have calculated the value of V3 here. So V3 will be equal to V2 into T2 raised to power T3 raised to power 1 over 1 by over n minus 1. Now you can easily put the values of temperature here, okay, and then calculate the value of V3, which comes out to be 0.756 meter cubes. Similarly, from this particular equation, you can always calculate the value of pressure P3. Okay, it's a simple algebra with the help of which you can put all the values and calculate the final value of the pressure, which comes out to be 25.93 kilopascal. So basically this completes our this table here. This was the initial table. In the second case, this value was calculated here, and this is the final table which shows all the values have been calculated. Now right now it is nearly end of the lecture. So what I will do, this is the next slide. I will discuss about it later on, but what you do, you try to understand it from these values, actually how I have drawn this PV diagram here. Okay, just try to understand this particular case, how the PV diagram has been drawn. You can see it in the video lecture, the last 5 minutes you can see. Then I will just turn over the slides so that when you see the lecture on the YouTube, I will also share the PPTs. You can read it from there also. Just try to complete this numerical problem. Now I have written all the equations here, how to calculate the various values here. Okay. See, you have already understood the concept of the first law of thermodynamics, and you know how to calculate the values of work transfer, heat transfer, and change in internal energy. Once you know all the values of different parameters like pressure, volume, and temperature at 3 state points, you can easily calculate the values of work, heat transfer, and delta U. So this is what I have depicted here in this problem. Here the solution is given to you. So what you can do, you can see the solution either on the YouTube or through the PPT, and then solve it. So this is a very important numerical problem. Okay, so this is the final table. This is also very important table. You should try to understand it and let me know uh, whether you have understood it or not. Now one more thing I would like to tell you is that there will be your class test 1 next week. Will it be okay for you on Wednesday? Will it be okay for you?
Okay.
Yes,
I,
I think so.
I don't know
Means
because there is a new student, so I don't know.
So you are a new
Yeah,
student.
No,
there is.
I'm not a new student. I'm talking about the new student. So I don't
Okay,
know
you
me.
can't, you cannot say about the new student. So okay, what we can do is I can keep this test on 7th, Monday is 18th actually. 18th Monday will be okay.
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 Today is
Okay.
6th, 6th,
1-8.
1/8. Yes, 18th of this month, Monday. So today it's 6th. Still you have 12 days to prepare. If there are some new students who have joined, they can go through the lectures and we can have our class test 1 on 18th of January. Okay.
Okay.
So
Okay,
what you
teacher.
can do is I will give you first three chapters. There will be first three chapters which will be coming in this. So first chapter is actually basics of thermodynamics, which in which process etc. has been discussed. Then temperature, and the third chapter is on work and heat transfer. Simple basically. And I will also talk to your other teacher whether he agrees for Monday or not. I will ask him. So he will also share some questions. So I will tell you what will be the pattern of the question paper. Okay.
Okay.
And one
So
more.
the Monday 18.
Monday 18th. Yes. But I have to
Okay.
talk to your other teacher also.
Okay, sir.
Okay.
Thank you.
Okay. Okay. And I will let you
Sir,
know.
I'm sorry, but sir, the test will be on the same day with the
What did you?
mechanical engineering part B. Part B, the test will be
Yeah.
the same day, part B and part B.
Yes. 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 It will be a 1 hour test in which part A and part B questions both will be asked. It will be a 20 marks test. Okay. So
Yes, understood.
what I will do next Monday, coming Monday, I will prepare a demo test for you. Say 10-15 minutes demo test for you that I will take. So you are familiar with the test, how to give it, how to appear for it. That would be easy for you to understand. So you would be having
Okay.
1 week. So all of you must have your cameras switched on during the test part. Okay.
Yes.
Okay. So now just wait for
It
two
will
minutes.
be. It's we will. You will give us and write in here and submit and send in Google Classroom.
I will let you know.